All right, this is Mr. McCord's chemistry class. We're in Unit 8, and we're looking at doing some practice problems with the ideal gas law. So let's look at a problem you might see on one of your assignments, either close to it or maybe dead on if you're lucky. An average adult can hold about 6.00 liters of air in their lungs. Suppose an adult breathed in air mixture that had a molar mass of 28.90 grams per mole to completely fill their lungs. So if the temperature inside their lungs was 37.02 degrees Celsius and the pressure was 103.2 kPa, calculate the grams of the air inside the person's lungs. Okay, so we've got some variables laid out here. If we kind of pick through the story part of the problem, we should have a pressure of about 103.2 kilopascals, kPa. The volume inside the lungs is about 6.00 liters, if we're assuming we can fill them all the way up. We don't have a value of moles, an amount of gas N. Right? We're going to pick a gas constant R to fix our pressure unit. Right? Since we're doing this in kPa, we're going to pick an R constant that also works for kPa. And then our temperature is given as 37.02 degrees Celsius. Now remember, we cannot use Celsius in the ideal gas law or any of the gas laws, so we've got to convert that to Kelvin by bumping it up by 273.15. Right? Now also, the problem asks us to figure out how many grams of this stuff we have. We're going to solve for moles, which we can then convert into grams. Okay? So if you see grams, you're like, oh, this equation doesn't have grams in it. Don't freak out. Okay? We will get there. We're going to hit moles first. If you can get to moles and you know what the stuff is made of, you can get the molar mass. We can convert it. In this case, we don't even have to add it up. They tell us the molar mass right out. Okay, so I've got this stuff plugged in now. Our ideal gas law is pressure times volume equals moles times our gas constant times our temperature. So PV equals nRT, or PivNArt, however you want to say it. Okay, so I plug in everything I have, and I can look for N by getting it alone. That means I've got to do some algebra to get this stuff away. Okay, now there are a couple ways you can do this, but the way I'm going to tidy this up is by multiplying everything that I can, crunch all my numbers together, and then I'm going to solve for my N here. So my units are going to look a little bit nasty. Remember, if you get stuck with the units and you don't really understand how they cancel, worst comes to worse, just know, hey, I'm looking for moles, so I better end up with moles. That's going to be my unit. Okay, you can kind of fall back on that. Understanding units is great, but don't make it kill all your confidence if you don't get it. It'll come to you. Okay, so let's condense. Okay, my 103.2 times 6 is going to give me a number around 600-ish. 3.2 times 6. 619.2. And my units are kPa and liters. Over here, my 8.31 times my 310.17. Let's see. This is a big number. 2,577.51. And my Kelvin units down here at bottom, and the ones on top over here are going to cancel. So what I've got left over here is kPa in liters per mole. Okay, N is still there. So, to get N alone, I've got to get rid of this. Right now, these are being multiplied. So I need to divide them to cancel them out. Okay? If you like a way to quicken up your math, okay? If you don't like having to divide on both sides or multiply on both sides, to undo something that's being multiplied, think of it as dividing it over to the other side. Okay? Or if you're trying to get rid of something on bottom, think of it as multiplying it up to the other side. Okay? Now, it kind of skips the whole canceling step, so if you like seeing that, maybe you don't want to do this. But if you like to speed up the math process, I kind of like doing that. So I'm going to kind of divide that under. But I also want to show how my units cancel, so I'm going to do it the long way. Okay, on the right side, this whole thing goes away, leaving just my n. All right? On the left side, KPA divided by KPA cancels. Liters over liters cancels. And then my moles on the bottom of a fraction bar, and then on the bottom of another fraction bar, flips back to the top. Kind of over one undoes that. So it's being divided, so it's going to be now multiplied. It's going to be up on top. My units should be moles. All I have to do is take this number, 619.2, divided by this 2,577.51. Do that my calculator. All right. We get a pretty small number, which we expect. Moles are an amount of a chemical. All right? Gases take up a lot of space compared to how much there actually is, so we should expect to get a pretty small number unless we're dealing with a very large amount of gas. My answer comes out to be about 0.24 moles of gas. Okay? Now you may remember, this is part of it, but we want to figure out how many grams of that gas is. So we're not quite done with this. All right? I want to convert this into grams by getting rid of moles. Now, air is not something you find just on the periodic table. It's a mixture of gases that we would find. Okay? So in this problem, I have given you the molar mass of that mixture of air based on the percentages of all the stuff in it. And I just kind of don't worry about it. Okay? So since our molar mass in this case is 28.90 grams per mole, all right, I want moles on bottom, so they'll cancel. Therefore, I want my new unit of grams on top. And there are 28.90 grams per mole. We're one with moles. My moles units should cancel out, leaving just grams of air. So if I take 0.24 times 28.90 divided by 1, I should get my answer, which comes out to be about 6.94-ish grams of air. Some problems will have you start in grams and then work out of it. So in that case, you would kind of start here, undo your grams, your fraction bar would look something upside down of that, and then you'd work through the process. Okay, let's do a harder example. Something that starts with the ideal gas law, where we are finding a pressure, volume, temperature, amount, something, okay, in the moment, But then something changes. We go and mess with the temperature or the volume of the pressure, and we see how that other missing variable comes out on the other side. Okay, so let's do an example. Okay, a chemist has 1.42 moles of dichlorine gas in a 10.0 liter tank at a temperature of 27 degrees Celsius. The first thing we want to do is figure out the pressure inside the tank in atmospheres. Okay, so let's try that. Okay, I've got stuff plugged in, all right, into my ideal gas law. Okay, I've converted my temperature into Kelvin so I can use it properly and get the right answer. I've picked an R constant to go with my pressure unit. In this case, I have been asked to find it in atmospheres. So I just picked my R constant to fit that. Okay, and now all I have to do is solve for the pressure. Now the question also mentions what the gas is made of. It's dichlorine, that's Cl2. We don't have to convert into or out of grams for this. We already have the moles that we need. So we don't really need that little factoid. Whether it's Cl2 or H2 or C3H8 doesn't really affect our calculation here. Okay, so let's do a little bit of math. You may also notice I've left out my units this time. I know I'm searching for pressure in atmospheres, and as long as I do my math right, it should be fine. So this will just save me some time. I don't have to worry about canceling out all the units and stuff like that. Don't tell anyone. Don't tell the math police. I'm not involving units here. Okay, so to solve for pressure, I want to condense all these numbers here. And I also want to get this away from my pressure value. So let's do that. I'm going to condense these first. Multiply 1.42 times 0.0821 times 300.15. Calculator. There it is. Figure it out. 0.0821 times 300.15. All right, I get 34.999-ish. 34.99. Okay, that's still equal to P times the 10 on the left side. Okay, to get P alone, I need to get rid of that 10. So I'm going to take this and divide it on both sides. Now, I mentioned that shortcut before. I'm going to do it in this problem. I'm basically going to act like I'm just dividing this underneath here, and this is going away. Okay, same result, kind of skips a step a little bit, but the math works out the same. We're just not showing that we're dividing it on both sides. I'm just saying it's going to go away here. I'm tossing it under here. Okay, so my P should be equal to 34.99 divided by 10. So if my mental math is good enough, 34.99 divided by 10 should come out to be about 3.499. Since I'm solving for pressure, this is in atmospheres, because that's what I'm looking for. And it matches the R constant that I picked. Okay, so that's one part of this problem. However, you might remember, there's another part to this. We want to see not only what the pressure is in this moment, but we're going to go mess with something now. We're going to change up what the gas is like. Okay, something has happened inside our tank that has caused the pressure to change. All right, the new pressure that we reach is 4.25 atmospheres. All right, so this pressure that we just found was the original pressure before any change happened. Okay, before, when we did gas laws, we had some original variable. We called it a little 1, so like P1 or T1 or something like that. So let's show that. I found it to be 3.499-ish atmospheres. And specifically, this is my original pressure, and I'm going to call that P1. Okay, So my P1 went from 3.499 atmospheres to this new pressure we're going to call P2, which was 4.25 atmospheres. Now, everything else is held constant except the temperature. So we want to find out what that new temperature is. Before, in the ideal gas law, we started at 300.15 Kelvin. So that's my original temperature. We call that T1. So let's label that. So if I'm trying to find this new temperature, that's what we would call the T2. I'm trying to find this new temperature. Okay? So the gas law I want now has to do with a before and after, and it has to do with pressure and temperature at the same time. So I want Gay-Lussac's law, right? All I have to do is plug in what I've got and figure out what that new temperature will be. So we pick gas laws that are most suited to our situation. In this case, we're using Gay-Lussac's law. Okay, so we have this problem rewritten to fit Gay-Lussac's law, where we've got our original pressure and temperature over here. Right? We solved for this pressure. We were given this temperature. Right? We were also given that we reach this new pressure, and we want to figure out what temperature it's at once that change has been made. Okay? So just a little bit more algebra. And part of the problem was figuring out what gas law to use to fit this. Now, this one's kind of nasty because one of the variables that we're trying to figure out is on the bottom of a fraction. That's kind of annoying because we can't solve for it that way. We need it up on top. Okay? In the problem before, I showed how I don't like to always show out all the math. I kind of shortcut it. So I'm going to do that in this case too. And it's going to make dealing with this guy on bottom a little bit easier. Since this is being divided, and I don't want it to be down there, the way I would undo that is to multiply it on both sides. But instead of showing the multiplying on both sides and then this just cancels out, I'm going to show this by essentially saying I'm multiplying it to the other side. I'm kind of carrying it over. If it was on the bottom, it now goes up to the top. If it was on the top, it now goes down to the bottom. So my T2 has been multiplied to the top over here, which means it goes away over on the right. Okay. Now my T2 is in the place where I want it, but it's got all this stuff around it, which I don't want. Okay. So let's rewrite this a little bit so I can get rid of the other junk. Now, I want to get my T2 alone. So I need to get rid of my 3.499 atmospheres and my 300.15 Kelvin. So, just like before, instead of stepping through the whole process, I'm shortcutting this. The 300.15 I want to get rid of is being divided. So, to undo it, I'm going to multiply it over to the other side. Cancels out here. And it's now multiplied on top over on the right. This 3.499 is being multiplied, so to get rid of it, I need to divide it. So I'm going to divide it under to the other side. I'm going to take it over that way. Which means I get rid of it over here, and it's now being divided over here. Looks a little messy, but it's way faster. Okay, so those are gone. I've only got T2 on the left side. 4.25 times 300.15 divided by 3.499 should be my answer, and my units should cancel out. I get rid of my atmospheres. Kelvin stays. So let's multiply this out. 4.25 times 300.15 divided by 3.499. All right. My new temperature my T2 is going to solve out to be, all this crunched together, about 364.57 Kelvin. And this matches our expectation of Gay-Lussac's law. If pressure is going up, temperature has to be going up with it. Our pressure got bigger, so our temperature should also get bigger, and it did.